Hi everybody, we've got two worksheets to complete and I thought that I would do one problem on each worksheet with you. All right, so the first one we're going to look at is notes, functional values, limits, and discontinuous graphs. All right, so we've got this discontinuous graph over here, and my software program didn't put arrows at the end of this graph and the other end of this graph here. And sorry, it's kind of hard to see, but hopefully you're doing okay with it. All right, so we want to talk about limits. We want to talk about functional values and limits. And with regard to limits, a nice, well-behaved graph, one that's continuous, that you never have to lift your pencil on, there's not anything interesting that's happening on that type of graph. As a matter of fact, one would say that the limit exists at every x value on a continuous graph. So that's kind of boring. We want to kind of spice it up a little bit. So that's why we take a look at discontinuous graphs, specifically ones that have point discontinuities, infinite discontinuities, and jump discontinuities. All right, so over here, I'm going to do this first problem with you, which contains all these questions right here. The way I have it organized is vertically, so just kind of want you to see that we're going to work on problems going down as suggested by the lettering. All right, so for each graph, find the requested information. If we have a DNE, if we end up with a does not exist situation, we want to explain why. So go ahead and write that in. All right, question A, we're used to this. This is comfortable, this is old. We've been doing this for years. This is saying find the y value when x is -2. So this is a functional value. So let's go to where x is -2. Let's look up, let's look down, and when we connect to the graph, which we will up here at this filled in circle, our functional value is actually going to be +2. And we're done. It's about being, functional values are about being specifically at this x value, looking up or down. However, when we go to the limit notation, and notice that underneath limit, we have x approaches. This is not x equals -2. This is saying x approaches -2, and this little superscript is telling us from the left of x equals -2. What are the y values' intended height? So what I would suggest on this is not a functional value, but go ahead and real quickly get on the graph at x equals -2, but slightly move to the left. All right, you want to move just slightly, not too far away, just slightly to the left. We don't want to be at x equals -2. That's this notation right here. So at x equals -2, we're going to go right to the left of it as suggested by that superscript. Now, at this point, let's look up, let's look down. Oh wait, there's the graph up here. So let's jump on the graph where this x coordinate is close to -2, but let's move towards where x is getting closer and closer and closer to -2. So that means we'd have to travel up. Well, what's the intended height? Whether or not that circle's filled in doesn't matter. This graph suggests that whether I end in a filled in circle or an open circle, that my intended height is up to 2. So we say that this is a one-sided limit and the y values are approaching 2. So we can have one-sided limits that exist. All right, this is the limit as x approaches -2, but now from the right. So remember, this is not x equals -2, it's approaches. So, but go ahead and jump on the x-axis at x equals -2, but move to the right of it. Real close, this is too far away over here. At x values that are close to -2, but to the right of it, now we're going to have to look down here because that's where the graph is. This point would have an x coordinate that's close to -2. Now, what if you wanted the coordinates of points to get closer, the x coordinates of points to get closer to -2? Then we're going to have to start traveling down. Otherwise, if you start traveling up, your x values are getting further away from -2. So as you travel downward, I see an open circle. I don't care if it's an open or a closed circle. That's a functional value question. I just want to say, what is this part of the graph approaching? Well, this part of the graph is approaching y values of -1. So these two statements are fine. These two statements mean that the one-sided limits from the left and the right exist, and they're these numbers. But look at question D. Question D now says the limit as x approaches -2, but it doesn't have the superscript of positive or negative up here. which means that it's implied that we would have already looked at behavior of this graph as x approaches -2 from both sides, the left and the right. We did that by doing a recording up here. Well, the limit doesn't exist if the two pieces of the graph aren't coming into the same y value, whether that point's there or not. So the total complete limit does not exist. Because we have a graph to the left and to the right of x equals -2, and those one-sided limits are equal to these values, and these values are not the same, we say the limit itself does not exist. Well, in our case, it's either going to be an infinite or a jump discontinuity if a limit doesn't exist. We can see it's just like a step up. This is a jump. So it says if d and e explain y. So the limit does not exist because these two numbers are not equal. But we know that, but we want to use the notation. So I think it's good that you practice the notation. So the limit as x approaches -2 from the left, don't forget your function, the name of your graph, does not equal the right limit. And try and write this real carefully where you have the limit and then this statement down here below it, and then the f of x is just right off to the side of limit. All right, let's look at this next column right here. Okay, we're still talking about this f graph. Okay, now look at the input value of 0, 0, 0, 0. So now if I just kind of by inspection kind of look at this graph at x equals 0, well, this graph is well behaved here. It's continuous. There's not a point discontinuity, not a jump discontinuity, not an infinite discontinuity. The function's going to exist at specifically x equals 0, and the two parts of the graph are coming into that same point that exists there. So what's f of 0? Well, the functional value is exactly 1. What's the limit as you approach 0 from the left? Well, again, remember, here's 0, move to the left of it, jump on the graph and start going towards your x values getting closer to 0. The intended height is 1. Likewise, the right-hand limit, 0 from the right, that's a plus sign. If I'm to the right of 0, I jump on the graph, but I'm going to have to travel back down this way. So what's the intended height as I get closer to x equals 0? It's still 1. So because these two left and right-hand limits are equal, then we know that the graph, or the limit does exist. So this is this part of the graph is just boring. There's nothing interesting happening there. So the limit's going to exist and it's going to equal the functional value up here. All right, this last column all deals with behavior near x equals 3 as suggested by the notation. So come over here and just kind of inspect it. All right, I don't see an infinite or a jump discontinuity. I see a removable discontinuity that I call a point discontinuity. Okay, let's get the functional value first. So f of 3. Well, it's not at the open circle. The y value is exactly -1 because I'm standing exactly at x equals 3. All right, what's the left limit as x approaches 3 from the left? Well, as you approach x values close to 3 from the left, the intended height is 0. Okay, what's the right-hand limit? All right, you're to the right of 3, you jump on the graph, you start traveling down, get closer and closer. You don't want to be equal to 3 because that's this question. A limit is the idea of just approaching it. Well, my y value is also going into 0. Does the limit exist as x approaches 3? Yes, it does. It doesn't matter what the functional value is. The limit exists, and the limit is 0. So a limit will exist even though there's an open circle here, regardless whether there's another point or not. But at a point discontinuity, the graphs are coming in. The only thing that's missing is that one point. And that point's notation is denoted with functional value. Okay, limits just means it's approaching whether there's a point there or not. So hope this helps. Okay, as an example for this worksheet, go ahead and complete the second and third question down here with the questions that belong to each of those graphs. Okay, we have one more worksheet, and I want to do one problem with you here. There's 3 problems on this worksheet, and I'm going to do the first one. I think, no, actually, I'm going to do problem 3, and I'm going to let you do problems 1 and 2. Because 3, I like that graph because it has all 3 different types of discontinuities that we talk about. Okay. Again, we have this discontinuous graph. It's not continuous. If it was, it'd be boring. We wouldn't even have an opportunity to talk about too many of these questions. I mean, we could, but the limit would exist everywhere. because the points are there. You never have to lift your pencil to draw the graph, so it's boring. All right, let's look at number 3. All right, studying this graph, I see that we have an infinite discontinuity at x equals -2. Okay, it looks like we have a jump discontinuity at x equals 1. And over here at x equals 5, it looks like we have a point discontinuity. All right, let's answer these questions up here at the top first. All right, so what's f of -5? Well, x equals -5 is over here. If I look up, it looks like this part of the graph is, it exists. The y value is 1. We're done. As a matter of fact, I'm going to skip and go down here. Now, instead of doing in column format, my organization was in row format. So let's kind of go across on this worksheet. What's the limit as x approaches -5 from the left? Well, here's -5, be to the left of it, jump on the graph, and then start traveling to where your x values would be at -5, but not there. Well, the intended height is right there at that y value of 1. All right, so what's the limit as x approaches -5 from the right? -5 to the right of it, jump on the graph, but I want to go back down to where x is getting closer and closer to -5, all the while looking at the y values going to 1. Because these two limits, left and right-hand limits, are equal, or they exist, and they're equal, then we say that the limit does exist and it's 1. All right, f of -2, okay, x equals -2 is here. I'm looking up, I'm looking down. I know there's a vertical asymptote, but sometimes they'll throw a random point in at you. And if they throw a random point in at you on a vertical asymptote, that would be the functional value. But in this case, there's not a point. So f of -2 does not exist. Why? We're going to explain does not exist either. Oh, f of -2 does not exist. Pardon me. Well, for the simple reason that there's no y when x is -2. No y when x equals -2. So anytime you have a functional value question, it's simply, anytime you have a functional value question and the answer is does not exist, there's just no y that belongs to that x. That's the only justification. That's it. The limit justification of DNEs are a little different depending upon if you have a jump or you have an infinite discontinuity. All right, let's go to row 2. What's the limit as x approaches -2 from the left? Well, to the left of -2 is here. I jump on the graph. I have to move upward to get to stay on points where x values are getting closer to -2. I'm increasing without bound. The left limit is positive infinity. Okay, well, as you approach -2 from the right, you're on this part of the graph, and the graph is going down, getting larger, well, more negative, I guess. It's negative infinity. Neither one of these limits exists, does not exist. I'm just going to put a DNE and a DNE here because we don't go to numbers. In order for a limit to exist, it has to go to a constant number, some kind of leveling off. So then over here, automatically, what's the limit as x approaches -2? It does not exist either. Why? Now we're going to justify. On an infinite discontinuity, it's because we're going to re-record what we found over here. The limit as x approaches -2, and I'm going to leave off the superscript, okay, of the function f of x is, well, on one side it's positive infinity and on the other it's negative. So I'll just stack that as plus minus infinity. So the justification of why this limit does not exist is because the limit as x approaches -2 goes to positive and negative infinity. And this is notation that we write that represents the words infinite discontinuity. All right, so now let's go to f of 1. What's the functional value when x is 1? Well, I'm looking up, I'm looking down, and guess what? There's no filled in circle, so there is no y value when x is 1. So let's justify. And this time I put the word value. Over here I didn't. It's probably a better, description when you put no y value, but no y is fine. All right, so let's come down here to this row. Okay, what's the limit of the function as x approaches 1 from the left? So here's 1, here's to the left. If I jump on the graph right here, The intended height is to this open circle. It could have been closed, I don't care. The intended height is 1. What's the limit as x approaches positive 1 from the right? Well, here's to the right of 1. I jump on the graph. For me to get closer to x values of 1, I have to move on the graph this way. The intended height here is going to be at a y value of 2. So one-sided limits can exist like this, but then when it comes to this question, what's the limit as x approaches 1 of the function? Well, that's a does not exist. And the justification, like on the other worksheet, is because the left limit does not equal the right limit. And I want you guys to write this down because it's good practice for you to write it. Writing is important. Just get the practice. So we got the left limit does not equal the right limit. And don't forget your f of x. All right, and the last one, what's f of 5? Okay, well, when x is 5, I can stand there. I can plant my feet right here. I'm not, a limit is approaching, but 5, I have to stand here. That's what this notation means. I look up and look down. There's no y value. So the functional value does not exist. Before we answer these questions, I want you to think in your brain, so is the limit going to exist at the point discontinuity? Are the two ends of the graph that meet at that open circle, that point discontinuity, are they going into the same y value? Yeah. What's the limit as you approach 5 from the left? Well, the intended height is to that open circle, which is 5. This right-hand limit is also 5. So because the left and right-hand limits are equal, then the limit exists, and it's equal to 5. All right, and the final question that falls below each of these 3 problems is this. It says, identify the values of c for which the limit as x approaches that number c. C is just a number, okay? Identify the values of c for which the limit as x approaches c of the function exists. Identify the values of c for which the limit, well, those were redundant words. Sorry about that. Exists. So I think a better way to think about this question is, okay, it's asking me at what values of c, at what x values does the limit exist? Well, the limit exists anywhere that the graph doesn't have a jump or an infinite discontinuity. So I always think, okay, well, what c values or x values, okay, would the limit not exist, because it's easier to represent, you know, the answer by thinking about what I need to exclude from all real numbers. So for me, I'm going to respond to this question, and I'm going to say the limit as x approaches c of this function exists on, well, the only 2 x values that this limit doesn't exist is at x equals -2 and x equals 1. So how do I remove the x values of -2 and +1 from the set of all real numbers? That limit exists everywhere else at x equals -5, x equals -4, x equals -3, etc. Right, we're going to use interval notation. So the limit exists all the way from -infinity, because this graph suggests that it keeps going with no breaks, up until the first x value where the limit doesn't exist, which is -2. I'm going to put a comma. You can do a union. And then again, the limit will exist from -2 to 1. And then again from 1 to all x values to infinity. So think about where the limit doesn't exist, find those x values based on the graph, and then pull those x values out of -infinity to +infinity using interval notation. So I hope this video should help you go and finish the rest of the worksheets pretty quickly.